Thank you all. Let's get started. So my name is Henry Joshua. I've had about 20 years of automotive experience at General Motors, Stellantis, AVL, and now I'm in the semiconductor and tech industry since the last, actually since this
Sir,
year. So
I'm sorry,
sure.
GIRW then, sir.
Vivek, you asked me something?
I'm sorry, sir. It's a crosstalk. Sorry.
Okay. Yeah, so that's not a problem. So yeah, I think we are here with the motivation to share know-how. So please do make use of the opportunity and feel free to interact. It's more of a conversation than presentation, right? So that's my short background, but more important than my background, I want to introduce the primary presenters here today. There are three of them. So I will start with Dr. Anantanarayanan Velu, is an educationalist. I think I'm going in the same order of the presenters. So he's an educationalist, technologist, industrial automation, and IoT expert. He's serving as an associate professor at Amrita School of Computing in Coimbatore. He also leads the IoT and cyber physical team, trust area group of the School of Computing there. Then we also have Dr. Girish Kumar T. He's an AI and ML expert and serves as an associate professor at Amrita School of Computing, Coimbatore as well. And he leads the research groups and include machine learning, algorithms, and robotics. Following them, the paper publisher or my primary contact and the primary presenter today will be Ms. Sri Kalaivani Paneerselvam. She is an environmental enthusiast and a strategic architect. She actually works as an assistant consultant at Tata Consultancy Services, and she has more than a decade of experience in creating digital and intelligent IoT solutions in the power plant and automotive domain. So it's these days, I mean, both the domains are getting much more closer. So she comes with an excellent wealth of broad experience as well. So yeah, so let's get started. But let me ask a question. Why wireless BMS? Does anyone know? I mean, BMS is kind of like the brain of the battery, right? So there is a control system, let it be of a safety. There are three primary goals, right? Safety, performance, and intelligence. So let me throw out a question. Why wireless? Why go wireless? What motivates us? Going wireless isn't actually so new. You know, we went from a wired phone to a wireless smartphone. We went from a wired microphone to a wireless microphone, and even the internet. I don't know how many people still use Ethernet cables. But going wireless within a battery also brings certain important factors to be discussed, which is security, safety, cybersecurity, and performance is a very different because it's a safety critical application, right? But there are some strong motivations to go to wireless within a battery. Cost and the material, the wires are saved. And when the wires are removed, the weight of the battery goes down as well. But most importantly, the manufacturing process can be fully automated. When there is wired BMS, when the harnesses have to be laid in the battery, there's at least about 25 to 30% of additional time during the manufacturing process, and humans are required, which means it's also error prone and it takes more time. But with the wireless system, it's a lot more easier to manufacture and fully automate the procedures as well. Now, within wireless BMS, there are many different things, and the wireless BMS can be of when we speak of wireless, there are different protocols. But what we will focus today is an energy efficient, machine learning based, smart BLE implemented wireless battery management system for both hybrid electric vehicles and battery electric vehicles. So with that, I would like to hand over to the presenters. So yeah, let's get started. Kalai or Dr. Anand, one of you, I mean, whoever goes first, would you feel free to get started, please?
Yeah, there is a technical problem. Ananta is not able to unmute actually. Just
Okay.
a minute. Yeah.
Yeah, no problem. Every good presentations, every good seminars, every good sessions from World Economic Forum to here need to have this. That's what makes it good, right? Vivek, are you able to take a look at this, please?
Yes, sir. I've sent the request. They has to accept that. That's it, sir.
Yeah. Can you resend the request again, Vivek?
Yes, ma'am. Even now I have sent.
Okay.
So not a problem. So while we are looking at this, how many of you online actually are deep into EV vehicles or have interest in EV vehicles? Do you want to put a chat in there and say, yes, you are familiar, you're working on it, or you're studying it? Anyone wants to raise your hand? Type in something. Or if there's any specific questions, do you want to share? Okay, that's fine.
Yeah. I think there is some technical glitch from the professors. Maybe I'll
Okay.
just take it over.
Okay,
So
no problem.
yeah. Yeah. So what do we know about BMS and why is it so important, right? That is like let us kickstart like that discussion. Like most electric vehicle uses lithium ion batteries, and that too of different chemistries like lithium iron phosphate, lithium nickel cobalt, etc., and that operates between different voltage ranges, like it is between 400 to 800 volts. So it is kind of a high voltage system that needs a continuous monitoring. Say for example, the lithium battery ion batteries are vulnerable to higher temperatures. During charging and discharging, it is very important that we manage the thermal stability of the system between certain conditions to avoid battery fires. So this particular job is done by battery management system. So battery management system does a continuous monitoring of voltage, current, and temperature from each battery cell and triggers compensating actions like cell balancing, thermal management, or overcurrent or over voltage production unit. So all these are part of battery management system. Of course. And why do we need a wireless communication for battery management system? Like Henry was mentioning about the manufacturing time and all. Like when we talk about wired communication system, it requires a long, around 3 miles of wiring that is being implemented to connect these batteries, just to communicate, battery modules to communicate with each other, especially like during any damage to this wiring harness if it happens. So it incurs a lot of repair cost. So that increases the service cost incurred by the owner, as well as it is a kind of a extra process, which is a very difficult process to maintain in case of larger battery packs. So, and if we see the battery pack, it will have more than hundreds of cells connected in series or parallel to achieve that voltage requirement of 400 to 800 volts. If we talk about a bigger truck kind of applications, in that case even the voltage requirement might increase. That requires even complex communication system establishment between the wireless, between the battery modules basically. So this particular complexity can be reduced if we introduce a wireless communication system uh, to communicate between the battery modules with the master BMS module, which will take a proper decision on cell balancing or thermal control unit activation based on the monitored current and voltage from the battery modules. So this is the reason like why we are going for wireless communication replacement. And also like when we talk about battery swapping applications, so in that case the batteries have to be the modules have to be robust enough to immediately swap it without worrying about how it gets connected to the master BMS. So to avoid these things, the battery like wireless battery management system is very important. And also it reduces a lot of wiring hardness, and it will save around 15% volume of the battery pack. And the concepts that involves in establishing a very good control unit for this particular network, the wireless communication network that is established between the modules and the master BMS. These are the concepts actually: the software-defined radio, AML ensemble techniques, and then using these two concepts, we will implement this smart able implementation, which we will be seeing in the forthcoming slides. So what is software-defined radio? So whenever we take any hardware embedded system, we directly, like earlier, it used to be like a specific hardware is designed for a specific application. If it is a radio specific hardware, it will be used only for a particular to get it operated in a particular frequency range. Whereas now, since every other hardware system is being controlled using a software stack, so here in the radio or technology also, the software plays a very important role to control the radio frequency front end. So which based on the different communication parameter settings that we will pass it on to the RF front end, it will be adjusted to operate it either as a BLE or as a Wi-Fi device based on the settings that we pass. So this particular ability helps us to operate a a wireless hardware in different bandwidths basically, and it reduces the manufacturing time, and it reduces, like it brings in a single hardware production of a generic hardware that will be capable of or getting operated into different types of wireless devices. So this is the advantage of going for software defined architecture, and this is a kind of a progress of SDR over a period of last 30 years basically. And now we are at the sensor technology, utilizing, like combining our implementation with 5G and IoT. And of course, these are the advantages, like I mentioned. This with SDR, like signal processing is like done using the software controlled algorithm itself, and it is like more generic, and it is less specialized, which means this can be used across multiple applications, industry applications. And also, like since it is controlled by a software, it is like we will be able to do a real-time adjustments on the signal processing algorithms. Say, for example, the environment in which the communication will be established is it's not always ideal, right? We will have a lot of challenges that would disturb the communication between the devices. So to avoid that, how do we operate the devices in a very optimal operating region? So that is something we can do it with using a proper control algorithm using the controlled parameters. So that is possible because of the software defined radio hardwares actually. And also, like I mentioned earlier, it supports different communication standards and protocols, and it is of course ideal for IoT devices, wherein in a lot of other applications, industry applications, and the automotive applications, IoT plays a very important role. And this particular SDR concept is very much useful in IoT applications. And since it is controlled by a software stack, of course, when it comes to software, yes, of course, there has to be an a security implementation that will have to be considered. So since there is a software stack which controls these parameters, there is a scope of encryption, authentication, authorization, all these implementation also inside the software. So this will enable us to have a secured communication enabled. And this is the BLE stack, like we discussed earlier, an implementation of an SDR in which the host layer, there will be a host layer, which is nothing but an attribute, the GAT and GAP combination. So the GAP, which is nothing but the generic access profile, it will have all the profiles of devices that are connected to this Bluetooth device, which will enable us to do the security implementation like authorization or authentication in combination with the security manager protocol. And there is a GAT layer. So this GAT generic attribute profile will have the details of all the parameters that will be defined to be monitored. Say, for example, in our system, automotive battery management system, the current and voltage are the two important parameters to be continuously monitored, and then it should be transmitted to the other, the master BMS basically. So those two parameters will be defined in the GAT layer. And this particular host layer is a kind of a software stack, and it will be integrated with the hardware stack using the host controller interface, which means whatever network parameters, the physical layer is nothing but the data rate changes. Like, should I allow my device to operate on 1 Mbps speed or 2 Mbps speed? So all these deciding factors can be controlled easily using this host controller interface. So whatever control parameters values that we set here, it will be converted into, it will be uh, translated into the signals, so that the physical layer will be changed in a way that it will change between two different rates. This is just an example. Other than this, there are other parameters like connection interval, which will make the device to transmit the data at regular intervals. So all these are different parameters which will directly change, have a impact on the physical layer. And these are like software controlled parameters, a kind of a configurable parameters, we can say. And here you can see like there are three types of BLE devices. One is observer, like the broadcaster. Another one is scanner kind of. So broadcaster will continuously advertise so that the scanner can receive that data, and then it will establish connection between the devices. And this particular chart, I don't think it is visible completely, but this is just an kind of a roadmap for Bluetooth, the past few years, how it had evolved. And right now it is in BLE 5.2 version, which has around 3 data rate support. It supports 1 Mbps, 2 Mbps, and then 500 kbps. And adaptation of connection parameters, this is about how like using a software function, we will be able to control the physical layer is what is defined here. Here you can see like an example request, the connection parameter update request with a certain function that has a handle to the physical layer to send certain control parameter here, which will through HCI. I was talking about the host control interface, right? This is the software stack, and this is the BLE physical layer implementation. So this physical layer and link layer implementation basically. And this particular function, whatever is being sent through HCA, the host control interface, it will change the parameters in the master table, master BLE module. And then once it is updated, it is going to send in the successful event back to the master BLE module basically. So based on the HCI host control interface events and commands, this particular adaptation of connection parameters, which means the network parameters, can be achieved. And we can see it in the right that there is a central device and is connected to multiple peripheral devices. So there are two types of connections. One is connection oriented communication. Another one is connectionless communication. So in this particular case, where there is a central and there is a peripheral, this particular topology, we call it as connection oriented communication, wherein we send an acknowledgement for each data packet that we send from the slave device to the master device. The central one is the periphery, central, then one is the master BLE module, and the periphery is the slave modules, which is scattered across all the points from where the data has to be collected and sent to the central BLE module. So here, since why do we go for connection oriented communication? It is because to ensure that the data, we don't want any data lost. Okay, so whenever a data is lost, it will ensure that it will resend the data and get an acknowledgement for that. So that is the reason connection oriented communication is established. And about AML algorithms. So first we saw about this software defined radio concept, which will be used for this control algorithm implementation. And second one is the AML algorithm. So like we are going to use ensemble technique here, where what we will do here is like we will try to create multiple individual models, and we will use multiple individual models to make a prediction or decision. So that is how the ensemble technique works actually. Why do we have to combine these multiple models into single model? Like, why do we have to create these many models? Why not a single model will work? So this is because when we give a huge amount of data for a machine learning algorithm, it will try to create a generalized model which might not be giving an accurate results. To avoid that, there are certain conditions. Say, for example, for an operating range of 100 to 200, a particular model will be created. And an operation region from 200 to 300, another model will be created. And the final prediction output will be decided based on these multiple models that are created. So this is how the ensemble learning works actually. And of course, there are different types of ensemble techniques like bagging, boosting, stacking, and OOting. Look, like this is kind of a bagging algorithm wherein, like I mentioned, we will create a subset of the bigger data set, and each subset will create a model, and then this model, all using all the small base models, we will create a combined model, and this combined model we will use it for prediction. That is a bagging technique. Another one is called a boosting technique, wherein original data set will be used, and then we will create a model out of it, and using that model we will try to create another sample along with the original sample. There will be another data set sample that will be created, and using both we will train another model. It is kind of a sequential model creation, like until we reach a particular threshold of accuracy, this particular process will continue. And there is another way called stacking technique, wherein from the original training data itself, we will create a different model. So how do we create different models? It is about, we have KNN, we have regression model, we have decision tree. So all these different algorithms we will apply and create a different models here. And then we will train a new set of data and then create a second level model, and then we will try to use this particular final model to predict a particular value. So this is something we call it as stacking technique. Another one is a voting technique, wherein again, like we will use an individual model for like based out of the same data set with different algorithms. Based on the predicted value, we will check which one has the more probability of being that predicted result. So that is done something using like soft voting basically, which will have a particular result. So that we call it as like ensemble voting technique basically. And yes, now it is like we will discuss more about wireless battery management system. So when we talk about wireless implementation, what are the challenges that we would face in wireless communication? Anybody can ping in the chat? So what are the challenges that we will face? Okay. Yes. Let me give few challenges that we would face when we go implement wireless communication in battery management system. One is first one that we can think about is reliability. So we have to ensure a reliable communication is established between the battery modules and it stays, you know, intact all the time. I mean, during all the harsh operating conditions of the vehicle, it should be reliable. So that is one bigger challenge of wireless battery management system. Another one is about the security. So when we talk about security, the wireless management battery management system, it exposes a lot of potential threats. Example, unauthorized access, tampering, and data breaches. So we have to avoid, I mean, implement a proper authorization techniques here in order to avoid this security breaches. And there is another problem called interference and coexistence. So when we talk about wireless communication protocols, there are many devices around us that are operating in the same frequency region as it of the the protocol that we might implement in the BMS. So these particular interference issues have to be sorted out, and we have to ensure there is no degradation in the performance of communication between the battery modules. That is one thing. Another thing is about scalability. So whenever we implement a wireless topology for the communication between battery modules, we have different topology, like star topology we have, and we have like star topology with different hierarchy also. So when we talk, when we have to consider all these different topologies which will suit or enable the BMS system to scale up into multiple layers. Basically, if number of modules now it is 100, but in future it might go to 200 or 500 also. So a proper wireless topology should be chosen as per the number of battery modules that are used, and which means as per the number of communication devices basically used. So we have to ensure the scalability of the system. Yes. So this is a sample industry architecture with the automotive grade ICs specifically designed to high voltage and high temperature operations with over voltage and over current reduction systems. So here you can see like these are the different battery modules that are connected with a IC called BMIC 78714. So it basically monitors the batteries for over temperature and over voltage conditions, and immediately it will send an appropriate signal to the master BMS. So this is the master BMS which is connected with the BLE device. So here you can see that these are the monitoring devices connected directly to the battery modules. It will continuously monitor the temperature and voltage conditions, and this monitored values will be sent to the RF front end. Here, the RF front end that is used is like BLE. So this is again 14531 is another BLE SoC, which has other communication protocols. Like I mentioned, we are using software defined radio. So a single device will be able to establish multiple different communication protocols. Say, for example, here there is an SPI communication between the BMIC and the BLE device, whereas between the BLE RF front end over here and the master BMS, we are trying to communicate through Bluetooth low energy protocol. So a single RF front end is able to act in different protocols actually. So this is something uh, uh, about 14531 basically, and we can see here about the MCU RH850. So this is nothing but a microcontroller which will get the monitored details from these monitoring devices, and it will take the appropriate actuation. Say for example, if there is a over voltage or over current, immediately it will send an actuation here, and it will open the relay, which means it will disconnect the system so that we will avoid the battery fire. So these are all kind of we will call it as ASIL or D, the protection, the safety protocols actually. So this is kind of a safety system implementation from industrial perspective. So this is, I think, it would be clear. And yes, this is just an example. So based on which we have constructed a BLE network, and we try to analyze different network parameters. And here is the bandwidth diagram, like the of different, the categorization of different wireless protocols based on its range availability. And here, like, we are aware that the requirement of a battery management system is personal, it's a personal area network. So we will fall under this particular range, which between 10 to 100 meters radius basically. And many wireless technologies like Zigbee, Thread, Z-Wave, and all or like falling into this particular category. So to select a particular wireless technology, what we did was we did a comparative study between different wireless technology based on certain performance parameters. So here is a like resilience, like how far it will come back to its original form, even if it is like switched off or any kind of error happens. So in that case, it should again come back, and it should establish the connection with the master BMS, right? So all the slave modules should be able to communicate successfully to the master module. So that particular resilience factor we will consider. And retransmissions, number of retransmissions is like, since I was talking about connection oriented communication. So in that connection oriented communication, there has to be a proper acknowledgement between the data packet transfer. So if the data packet is failed, in that case, there will be a retransmission. So if I should choose a communication protocol which has lesser number of retransmissions. And about the packet loss, how much packet loss, how much bit error rate my packet will have, all these have to be considered. And there will be a overhead, and energy consumption also is an important parameter. And then RSSI. RSSI, of course, will directly proportional to the signal to noise ratio. So based on which we can predict how much would be the bit error rate and all. So based on these parameters, it is like we have taken BLE into consideration and Zigbee into consideration. And there is another comparison that we have done based on the frequency availability and the data rate that is given to us actually. Since it is a personal area network, I think 1 Mbps speed or 2 Mbps speed itself would be sufficient enough for the communication. And also, like, since it is operating in 2.5 gigahertz, there are more possibility that a Wi-Fi network which is operating with 2.5 gigahertz might cause some interference issues. So that experimentation also we had done in this thesis section. Yes, so the objective of this particular work is to construct a resilient wireless network for battery management system using Bluetooth low energy modules. And when we talk about any time constraint applications, we will be worried about the latency, right? So in this case, what we have done is we have kept a constraint on latency, and then we were analyzing the system under different RF interference. Say, for example, PRBLE is also something devices that will operate in the same frequency region. Also, the wireless Wi-Fi devices that I mentioned earlier will operate in the same frequency region. So, in the presence of all these devices, how is my network established network is performing? That is also something we were analyzing. Once the network parameters were analyzed, we were trying to come up with an control algorithm based on the AML model that we created using the observed parameters. So that what we did is we tried to create it as an automated network parameter adapter layer, which will change the parameter details by observing the current network parameters. So that is kind of an auto tune. It's kind of auto tuning the network basically. And by doing so, we were able to achieve lower power consumption and a lower number of retransmission. So these two we were able to achieve, which we will explain. So here is the hardware architecture that we used, and one different thing that we had used here is we ensured that we will use devices from different vendors basically. So here, if you see here, it is like we had used devices from NRF, which is from Nordic Semiconductors, and ESP32, which is from Expressive Systems. Yeah, Expressive Systems. So this, using this, we were actually trying to simulate the battery voltage and current details, and we were trying to establish a connection oriented communication with the master BMS module. So this master BMS module is also kind of like it was implemented in Raspberry Pi. Along with that, the BLE front end was connected, which acted as a master. And all these other BMS monitors were connected to the BLE modules, which acted as the peripheral devices. And this is kind of a star topology that we had implemented. So these are the devices used, like I mentioned, NRF devices from Nordic Semiconductors, and we had used expressive system devices ESP32 and Raspberry Pi for implementing the control algorithm, and we used power profiler kit, which was measuring the power from NRF device. It is like continuously it was trying to measure the power consumption of a BLE device, so that we will understand the power consumption of uh, the entire network, like how is it varying by varying the control parameters, the network performance parameter. And this is the test bed setup where we have a master module, like I mentioned, it is connected in a star topology. Uh, I've mentioned, it is the Raspberry Pi, which has the control algorithm. So the master module is connected to all the other slaves, and whichever modules that is highlighted in red, they are the interference modules, like which was simulating, which we were trying to simulate an interference scenario, like to understand how the network is performing. And you can see the power profiler kit here, which is continuously measuring the power consumption of a NRF module. So this is the software architecture basically, wherein the control layer, which is the physical layer, and the link layer is being controlled by the host layer, where the parameters, like the control parameters, like the connection interval is one such example. We will be continuously monitoring the latency of the system, and we will do a link quality estimation based on which we will send the proper commands. This These commands will change the network parameters to operate this entire network in a proper operating region. And this particular graph, the timing diagram, shows us it's the output of the power profiler kit. Power profiler kit, wherein it is clear that these are nothing but the data transmission periods during which there is a hike in the current consumption. So you can see the connection interval, it's nothing but the frequency at which the data is transmitted from the peripheral device to the master device. And this is a transmission period between which the actual data is being sent. All the other smaller spikes are nothing but it is it is just the heartbeat of the slave device. It is because in connection oriented communication, the devices should ensure that it stays connected. So I'm just declining this request for now. Yeah. So the slave devices will send a continuous heartbeat signals so that it stays connected to the master BMS. Whenever the data is available in the slave devices, only then the data will be transmitted to the master BMS. Yes, these are the network parameters. Like we mentioned, we are going to monitor the network parameters for a period of time, like data packet length. So what we will do, we will try to send different packets of different sizes, and then we will observe the performance in terms of latency. And latency is of course, the time between the client requesting for the data to the slave device, and the slave returns back the data to the master. So this particular time we measure it and we call it as latency. And there is a connection interval parameter that I have already mentioned. This is the frequency at which the data is being sent from the client again sends request for data to the server, and the server sends the data back to the client. Okay, which one do I call it as client? Which one do I call it as server? The client device is nothing but the master PLE module, and the server devices are nothing but the slave devices which are connected to the master. And at regular intervals, this particular request of data from the client happens, and the server will respond with the monitored temperature, current, and voltage values. And there is a retransmission factor which is proportional to the number of times the data packet has failed and then retransmission has happened. And there is another parameter called link quality parameter. It will determine the quality of the network based on number of retransmissions. So it's a kind of derived parameters. There are certain parameters which are raw parameters which we will monitor continuously, and then we will derive certain parameters using some calculations that we call it as this retransmission factor and link quality factor or such examples. And data rate is something it determines the rate at which the data is transmitted between the client and the server. And connection event is something the useful communication time within which the data is actually transferred. So this is a latency estimation, like how are we calculating the latency, right? So the link quality is estimated using latency, which is calculated based on the time difference between the data read request from the master. So here is the master client, which is master BLE. It is sending a request through the controller layer, and the slave devices will read the request, and then it will send the data back along with the event. So based on this event, we will be able to understand the latency. So for latency, for calculating the latency, we were using the real-time clock available in NRF module. So once the latency is calculated, we were trying to understand the retransmission factor through this particular mathematical computation. So you can see the latency is the total time, including the number of retransmissions that had happened, And along with that, like we are just subtracting the connection event, which is the useful time period at which the actual data has been transferred. So out of total latency that has happened, we are just dividing it with the connection interval, the frequency at which the data is being sent. So based on which we are arriving at the retransmission factor. And also like we are by rearranging the same equation and introducing the data packet length and fragment size, we are able to calculate the connection interval. What is the maximum connection interval that I need for a restricted number of retransmission, like allowed retransitions basically here. So by allowing certain number of retransmissions, we have a handle over the connection interval that can be changed dynamically in the network that is established. So by using this calculation, we are determining the retransmission factor, and by putting a restriction on the retransmission factor, we will be able to estimate a connection interval through this mathematical model. So there is a mathematical model which we are using for comparing it with the machine learning model, basically. So using this, we are this is the comparison mathematical model that we are using. And there is a link quality factor estimation, which, like, how do we calculate this? It is calculated based on number of worst latency divided by total number of latencies. This is nothing but we will monitor the network over a period of time. Say, for example, for the 20 observed parameters, observed latency instances, how many are the worst latency? Worst latency in the sense, like I mentioned, we have a constraint on the latency, right? We will set up latency as 200 milliseconds or 100 milliseconds as the constraint. So within that constraint, how much is my constraint violation has happened? A kind of a bad guy here. So number of bad days over total number of instances is what is calculated for link quality estimation. So if the link quality estimation is more, then it means we will have to control it in a way that by put a restriction on the retransmission factor, we will have to estimate a different connection interval. So that is how we will control the network's performance here. And this is the data set generated by varying different network parameters, like by varying different packet sizes, by changing different transmission power, by changing different data rates. It could be 1 Mbps or 2 Mbps. In both the data rates, we had observed this performance, network performance using latency and retransmission. And we had used predicted connection interval. This particular column you can ignore. I will explain actually. This particular current consumption we had measured using the power profiler kit. And latency, of course, like I mentioned, real-time clock of NRF device we had used, using which we measured latency. And retransmission factor is something we measured using the calculation I had explained. So out of which the initial connection interval that we had set was 7.5. This is just the predicted connection interval from the machine learning model that we created actually. This is the original data set using which a machine learning model was created. And that machine learning model was predicting certain connection interval, which led to a reduction in power consumption from 520 milliamps to 158 milliamps. You can see that around 1/3 of the current consumption is reduced, and also the number of latency violations are also reduced at a higher rate here, because with the default connection interval set, we are able to see a lot of latency violations. Here in this case, we are considering latency constraint of 100 milliseconds. So that much latency we are not allowing actually more than 100 milliseconds, because it is time critical application. And by applying a proper connection interval, we will be able to reduce the latency to a greater extent. And also, like you can see that retransmission factor is also highly reduced by changing to a proper connection interval estimated by the machine learning algorithm. So this is the derived data set. We can see that in the derived data set, we have categorized this particular original data set into a sub derived data set, wherein we are categorizing the connection intervals based on connection intervals, how much instances. Here in this case, we were simulating around some 10,000 data points. So out of 10,000 data points, how many instances are falling into the category of 0 to 100, which is like which is able to give us the latency between 0 to 100 is what is categorized into category 1. And between 100 to 200, we call it as like category 2. So why do we do this categorization is because whenever a machine learning model is going to predict a particular connection interval, we will use another classification model to understand if it is able to, that predicted connection interval will be able to help us achieve latency between 0 to 100 or 100 to 200. So get a kind of approval on the estimated connection interval, we are using another approval machine learning model, basically a classifier kind of thing, for which we are creating this particular data set. So two data sets we had created. One is the original data set from the raw data and the derived data, derived calculated parameter, and another data set, like it's a kind of derived data set itself based on the original data set. We do categorize data points into different categories and create a different data set. So this is the EDA, exploratory data analytics, that we had done, like kind of bivariate analysis between where we compare the retransmission factor by varying different values of connection interval. So by varying different connection intervals, we could observe that at a point between 40 to 60, we were able to achieve a very less number of retransmission. So by doing an exploratory data analysis, we were able to understand how the data, like how the trend changes and where is the effective or optimal operating region of the network, basically. So when we talk about network, it is about master BLE module connected with multiple slave BLEs. It's like with the overall network performance, we will be able to arrive at a region. If we operate the entire network in that region, we will be able to achieve a lesser number of retransmissions. So that also we verified, we simulated the data in both ideal condition as well as with the interference condition. So that is where we were able to get this plot. And another plot is about the connection interval versus latency. So here also we had what we had done is, well, like we had changed the connection interval from 10 to 70, and we were able to observe that the minimum latency we were able to achieve even with the shorter connection interval. So when the connection interval is shorter, it means it transmits the data at a faster rate. So which means like every 10 milliseconds, the data will be transmitted. So at that point in time also, we are able to achieve a lower latency, and also like at a connection interval between 40 to 60 also, around 46, we were able to achieve a lower latency by doing this. That is because the number of retransmissions, the congestion in the network is very less, because of which we are able to send the data at a lower latency. And also like we plotted the graph between current and the connection interval. And also it is very clear that as the number of times the data sent is reduced. So here compared with the connection interval of 10, like with a connection interval of somewhere around 46 or 45, we were able to reduce the power consumption at a greater extent from 700 to it has come around 200. It's around 1/3 of the power consumption of BLE module, like it is reduced. and we had verified the same with and without interference scenario. So all these analysis we had considered and figured out that this is the optimal operating region. If we will be able to achieve this, we will be able to achieve a lower power consumption. But it is not only lower power consumption, right? If we see here, for when the interference is more, uh, we are able to see that only at this operating region we are able to achieve the lower latency. So in that case, we have to adapt between different connection intervals uh, based on different interference conditions. So to do this adaptability, what we had done, we had created this prediction model. So based on the latency requirement of that system and number of retransmissions allowed, and based on the number of peripherals connected and data packet length, we were able to predict a proper connection interval in which, if we operate, we were able to achieve lower power consumption, lower latency, as well as lower number of retransmissions. So this prediction model that we created, we were able to get the proper connection interval with an accuracy of 99.7%. And once the connection interval is predicted, if we apply to the system, will it be able to operate the network in the optimal region, is also something that we had categorized the probability of maintaining the latency between certain ranges, right? So based on the given latency condition, this is also classified. The output of the previous model is given to the approval model, and after the approval model says like if it can be applied to the system, only then the HCI command is being sent to the controller layer. So this is the algorithm basically. So once we monitor the system for 50 instances with a constraint on latency and retransmission factor, we will calculate the number of the link quality factor first. Also, that like we discussed earlier, link quality factor will just keep the bad cases divided by total number of instances, the observed instances of latencies basically. So based on that, uh, we are taking into different decisions. Like one is like if at all uh, link quality factor is between 0.05 to 0.15, it means the network is operating in a very good region. So in that case, we don't do any action. We just do monitor for the next window. And if it is greater than 0.15, then we do predict a new connection interval with a lower retransmission factor. Because when the link quality factor is higher, it means number of retransmissions are more. So we are trying to reduce the number of retransmission here. And then if the link quality is very good, which means it is like less than 0.05, which means the link quality factor is very good. So what we are doing here is we are doing a little bit trade-off between the quality and the power consumption of the device. So by choosing a higher retransmission factor, we will be able to reduce the power consumption a lot. So that is from the graph, it will be clear. By using a higher connection interval here, sorry, by changing the connection interval to 10 or 8, we will be able to achieve lower latency, but with the sacrifice of retransmissions. More number of retransmissions are possible. So in that case, little bit of power consumption is increased. So this is something that we will do based on monitoring the link quality factor of the established network. So once the connection interval is estimated, it will be sent to the approver, and then the commands are being sent to the slave devices. So this is how the network is continuously monitored and the control parameters are changed in order to improve the performance of network at any point in time. It's a kind of automated control auto tuning algorithm that I was explaining in the earlier slide. So these are the results of the algorithm, where the ML based algorithm we were able to achieve a higher, the current consumption was greatly reduced here, both in ideal condition and interference condition. Similarly, the retransmission factors also, it is highly reduced for ML based algorithm. And similarly, this is the total results of the algorithm basically, where you can see like number of adaptations to achieve the optimal operating point it is very less in ML algorithm, whereas the latency violations are like also very less in ML based algorithm. Also, the average power consumption is also very less in ML based algorithm, and this was validated for different window sizes. So it is like by establishing an intelligent monitoring system and auto tuning algorithm, uh, we were able to achieve the optimal operating point faster than a generic mathematical model. So this is something we have concluded. And also like we were able to achieve a lower number of retransmissions of around 2 and lower number of power, like current consumption basically. So yes, this is like with respect to industrial application, the same algorithm can be established when a large number of BLE devices are like involved in the network also. And also like it can be connected, this particular algorithm can be hosted as a cloud service also. And when it comes to trucks with large number of BLE modules, like this particular algorithm can be used as a monitoring uh, uh, control algorithm basically. And also like we have done this experiment using devices from multiple vendors. So for a battery swapping scenario, we don't have to worry about BLE device from a different, I mean, should we use the BLE device from the same vendor is something we don't have to worry by using this algorithm. And also like yes, this same approach can be used across different wireless protocols. Yeah.
Excellent. Thank you, Kalai. That was a wonderful, fantastic overview and presentation. Was a good balance of deep dive and also the overview. Do we have any questions? I mean, there were quite a lot of good interactions as well. Do we have any questions for Ms. Kalai here? I think, I mean, we could take a couple of questions if it's there, as we are also pretty much on top of the hour. Kalai, quick question, just to give a chance. What was the technical difficulty with your professors? Is it fixed? I mean, maybe at least they could say a quick
Yes.
hello to the team.
Yes.
Yeah. Yeah, I think we should take
Yes.
a chance to, would be great to hear from them as well.
Yes. Ananta sir is available here with us.
Yeah.
Ananta sir, like, yeah, can we have a short discussion about the SDR? Hello.
Yeah, we could hear you, Kalai. I mean, I think
Yeah, let me. Yeah, Ananta sir, we are not able to hear you.
yeah, let me make a comment actually while this is going on. There was a very interesting point that Kalai touched upon, which is the second life of batteries. What's happening in the industry now is with EVs, and it's not only that environmental benefits that's, how do you say, from the fuel or the non-usage of high carbon fuel that's actually creating the environmental benefits, but with the battery, it's actually quite important to do the second lives. With that, having a wireless BMS gives a huge advantage to repair or to replace the modules. And this is something that's a huge advantage with the wireless BMS. It's so much more easier to replace and also to reuse and to go on. We have a hand raised. I mean, maybe we could, if the audio is allowed, we could hear, or you could also type in your point or question into the chat. Both are welcome. Kalai, do you want to pick this one up? The functions of HCI. So there's a question from GT Bakiraj.
Okay. Yeah, HCI is nothing but the host controller interface. It will help the controller to communicate with the host. Like host, I had mentioned about the software stack implementation of GAT and GAP layer, right? The profiles of devices that will be connected and the attributes that will be defined. Based on that, we can define the initial parameters like retransmission factor or the data rate and all, right? So the data rate definition we can define there in the software stack. And if we change it from 1 Mbps to 2 Mbps, that particular information can be passed on to the controller layer using HCI. I think I have answered, Bakiraj.
Yeah, thank you, Kalai. That was good as well. I mean, while I just want to make a couple of comments as well. The company I'm also part of, Analog Devices, is actually the market leader in WBMS. If anyone is wondering, okay, is a wireless BMS actually in production? Yes, actually with Analog Devices, we made the first production vehicles on road with wireless BMS. I don't know if you are familiar with General Motors Hummer cars, and the Hummer EVs are actually working with wireless BMS from Analog Devices. I'm going to share a couple of links for people who are even more interested in knowing more about wireless devices that you could also read through. So I'll just post it in the chat for everyone to look. And if there's any other questions, you are also welcome to contact us later. So, Kalai, I think, should we then wrap up if Mr. Anant is not able to connect, unfortunately?
Yes, there is some technical issue, it seems. So, because of which sir is not able to. Actually, they are unmuting, but unfortunately, we are not able to hear them. But Girish sir is there. Let us.
Sure, yeah. Let's have a quick. Let's hear from.
Girish sir. Hello. I think he is also facing certain technical issue.
Okay, so then I would thank everyone for joining in the call. We will share the contacts later. If there's any other questions, you're welcome to contact us. With that, we will wrap up this morning session. Yeah. Thank you, everyone.